In this video, I want to talk a little bit about purine and pyrimidine nucleotide biosynthesis. Basically, how are purine and pyrimidine nucleotides made? So, where does that even happen? Where are they made? They're made in the cell cytosol. Okay, so the cytoplasm of the cell. Okay, and one important molecule involved in the synthesis of purines and pyrimidine nucleotides is PRPP, which is short for 5-phosphoribosyl 1-pyrophosphate. So the PRPP comes from those things I just underlined. So what is PRPP? It's an important precursor in the synthesis of those nucleotides. And it's also important in the synthesis of some amino acids as well, but we're not going to focus on that in this video. PRPP is made from ribose 5-phosphate, and that should be familiar. Where is this ribose 5-phosphate from? Where have we seen it before? Well, in a previous video, if you recall, we talked about it being one of the products of the pentose phosphate pathway. Pentose phosphate pathway. And we mentioned that the ribose 5-phosphate was important in nucleotide synthesis. And so here we're talking about exactly how that's happening. Okay. So ribose 5-phosphate gets an ATP attached to it, and that yields an AMP and the PRPP, which we're considering. So that reaction is catalyzed by ribose phosphate pyrophosphokinase. Pyrophosphokinase. Okay, so it's using an ATP to add a pyrophosphate to the ribose phosphate. So that makes sense. So ribose phosphate, pyrophosphokinase. So this is the ribose phosphate, and we're adding a pyrophosphate group to it from ATP, hence the kinase term there. So then when we get this PRPP, so this molecule here is actually what the PRPP looks like. So we have the phospholipase, right, comes from the R5P, which is why they're sort of in the same shade of blue here, and this pyrophosphate comes from ATP, the red, right? So we have a phospholipase and then a pyrophosphate. So that's what PRPP is. Now, what does PRPP actually do? Why is it important in the synthesis of purine and pyrimidine nucleotides? Well, it provides the phospholipase unit for both the purine and pyrimidine nucleotides. So this portion here, right, this portion here that we're talking about, this portion is important for the synthesis of purines and pyrimidines, right? So this is the pentose sugar portion and the phosphate portion for those nucleotides. So that's what PRPP does. It provides this portion for those nucleotides. So how does it do it? How does PRPP do that for purines specifically? So for purines, PRPP is involved in a long pathway with many steps, and what's important essentially is that PRPP is the precursor for this thing called inosine 5' monophosphate, which I've actually drawn here. I've cut off a little bit of it. There you go. This is inosine 5' monophosphate, or IMP. So it's like a excuse me, a nitrogenous base portion up here attached to a ribose with one phosphate group. I didn't draw that whole portion, but hopefully from the previous video you can kind of understand what it means here. So why is IMP important? Well, IMP is important because it's a precursor specifically for the purine nucleotides, which you should know as guanosine and adenine. Oh, excuse me, guanosine and adenosine. Sorry. So now IMP can be used to create the GMP or the AMP, and each of those, this GMP can go on to make GDP and GTP, and the AMP can go on to make ADP and ATP. So both of these pathways, either way you go, right, either way IMP goes, it's going to require energy. Okay, so what would we use for energy in either case? So in the case of GTP and ATP, if you recall, we've talked about both of these molecules being used for energy before. ATP, almost everyone knows that. ATP is the energy currency in a cell. We all know this, right? GTP is the lesser known, but it's still a common use of energy, right? GTP can be used much in the same way that ATP can be used for energy. And if you recall, we produce a GTP in the TCA cycle. So If we want to create GTP and we need a form of energy to power that production, are we going to use GTP? Well, probably not, right? If we're going to make GTP, why would we use GTP? That wouldn't make any sort of sense. You can't use up what you want to make. That doesn't even make sense, right? Especially since if you're making GTP, it probably means you don't have much around anyway, right? So you can't use GTP to make more GTP. So in the case up here, what we would use is to make GTP, we would use ATP. So ATP would power the production of GTP. So this ATP would turn into an AMP and a pyrophosphate group. Okay. So that actually this process requires ATP energy. On the flip side, though, if we want to create AMP or ATP, then are we going to use ATP for energy? Well, no. Again, that wouldn't make sense, right? If you're going to have ATP, if you have ATP, why would you make more? And if you don't have it, how can you use it to make it? Right? That makes no sense. You don't use what you want to make, to make what you want to make. That doesn't make any sense. I'm sure that might have confused some people, but the whole idea is if we want to make ATP, we're not going to use up ATP to make ATP. That wouldn't make any sense. So the energy form that we're using to power the production of ATP is GTP in this case. So the GTP will be converted to a GDP and a phosphate. Exactly why this ATP goes to an AMP and a pyrophosphate, and this GTP goes to a GDP and just an inorganic phosphate, I'm not exactly sure, but I'm sure the pathways themselves are a little bit different. So that's the sort of general answer to that question. So does that make sense, right? It should make sense because you want to use a different energy form to make another energy form. It wouldn't make sense to use one energy form to make that same energy form. So this entire process, of course, is regulated tightly. Now, why is that? The reason why is because we don't want to waste energy, obviously, right? These processes require energy in the form of GTP and ATP. We also don't want to waste nitrogen, right? These are nucleotides filled with nitrogen. We don't want to be wasteful with that nitrogen, right? Just want to be as efficient as possible. Especially since the waste products of these purines is this molecule here, and if you recall, we've covered that briefly. It's uric acid. Now, uric acid is not cool. Okay, too much uric acid production can lead to its deposition in joints. So in your, say your elbow joint, your knee joint, or even like your toe joints, just joints all over your body, right? And that condition is called gout. You may have heard of it, and that is very painful. Okay, so it makes sense that you would want to regulate this process tightly so that you don't have too many of this waste product, especially if it's going to accumulate in your joints and cause you a great deal of pain. Okay, so that's a sort of general overview about what goes on with purine nucleotide biosynthesis. But what about for pyrimidines? For pyrimidines, the process is a little bit different. So in pyrimidines, we start off by producing carbamyl phosphate from bicarbonate, glutamine, and some ATP. So we're producing carbamyl phosphate. So in this case, we're going to have this enzyme, carbamyl phosphate synthetase, which we've talked about in the urea cycle, but that was carbamyl phosphate synthetase 1. This one is carbamyl phosphate synthetase 2, or CPS2. So it's still making carbamyl phosphate, but in a slightly different way, and in this case it's involved in pyrimidine synthesis. So once we have this carbamyl phosphate, what we're going to do is we're going to take it and add it to this molecule here. What is this molecule here? Well, this is an amino acid that you should recognize. From the way it's drawn here, it might be a little bit tougher to recognize, but this is aspartate. Specifically, I'll put here L-aspartate. Okay. Now, L-aspartate is going to join carbamyl phosphate and produce this molecule here, and this molecule is called N-carbamyl L-aspartate. Excuse me. So this phosphate over here hops off, and this carbamyl portion gets attached to the L-aspartate here. Okay, so now what catalyzed that reaction? That was a reaction that we actually, that was an enzyme that we've talked about before. It's called ATCase, or aspartate transcarbamylase, right? And we talked about that in a previous video, and we talked about the regulation of that enzyme in the previous video. Check that out. If you look for ATCase, you'll talk in the enzyme regulation videos. You'll check it out. So then once we have this N-carbamyl L-aspartate around, we're going to lose some water to form this bond here to create. Actually, let me be specific there. We're losing this H2 and this O here, right? And then we get this molecule here, and this molecule is called dihydro, or I don't even know how to pronounce this. Dihydroorotate. Oh my goodness, I have no idea how to pronounce that. But this is what it is. Okay, that's really not too important. I'm not really too concerned with the pronunciation of this word, but what's important to understand is that notice that what we're doing here is that we're forming this ring, and this ring is basically the ring of the pyrimidine that we've talked about before. So that's what we're creating, and that's what we're concerned with. So this ring is created, and once that ring is created, there are a few more steps, but later on, PRPP comes around to provide the phospholribose unit. So then we create this here, which is, if you recognize this base up here, this is uracil, and this has a phosphate group and a ribose. So this is actually UMP, or uridine 5' monophosphate. So this UMP is a precursor to UTP, and from UTP you can actually create CTP, right, which is another pyrimidine nucleotide. So how is this a little bit different than purine synthesis? Well, in this case, the first thing that happens is that the ring is built, the ring of the pyrimidine is built, and then towards the end, PRPP adds the phospholribose unit. And then we have our pyrimidine nucleotides. So I hope that general overview is pretty helpful. One last thing, I am a tutor. If you live in Southern California, feel free to contact me via email at moofuniversity@gmail.com and see the description below for more details. Thank you for watching.